Alright, we're good. Alright, so today's just going to be a lecture on complex numbers. And complex numbers are very similar to vectors, because essentially we're looking at a y and an x portion, two components of of axes, essentially. But the only difference is this has a real and imaginary axis. So I guess a good way of drawing it would just be the unit circle. So we have the unit circle, right? And right here we could say that that's just 1. But this is this will be our real components, and this is our imaginary components. So this is the complex plane, right? So any point along here is going to give you a real portion and an imaginary portion, so that it looks like this. So z is equal to a plus bi, where I is the imaginary number. So I, sometimes you see notation j, and you'll see that a lot if you do, at least I've seen it a lot in electrical engineering, so you'll see it in AC currents, signals, so on. But this is equal to the square root of -1. So usually you've seen something where if you have a negative square root, that doesn't exist. Well, it exists, but it's a complex number. It's not just a real number. So if we draw a line, we call this line z, right? Z is equal to a, which is the, I'll just write it as the real. You just can't see this at all, can you? Can you see it over here if I write it right here? So z is equal to the real plus j times the imaginary portion of this. Does that make sense?
So what is j?
J is I, which is the square root of -1.
Oh, okay.
I'll write it up here. So I equals j, which equals the square root of -1. Yes.
J is what? J is I.
J is I.
Why can't you just say I?
Well, you'll see it in some the whole point is to apply it to engineering problems, right? You see it a lot, at least in electrical, where they use the notation J instead of I, but it's the same exact thing.
So they're interchangeable?
They're interchangeable. I and J are interchangeable. And right here, this formula that they have is just saying that the real part, is A in this equation, and B is the imaginary part.
You said A is the real part, right?
A is the real component, and B is our imaginary component. So this line, like we did in vectors, right? If we found the y part of the vector, right? That's part of the imaginary number. So that's going to be the imaginary portion, or B in this case. And our x component of this is just going to be the real portion, which is our A. So if we're given an angle, we'll be able to find the real and imaginary portion of that line, an angle and the length. And like this says, it's analogous to 2D vectors. It's essentially the same thing. The only thing that you have different is this j component, and your axes are different. Okay, this is an example. Okay, so this was the one-link robot, but now it's represented as a complex number. So we have our length L for the one link, and we found our component y, we have our angle, and like I was saying, the py portion is the imaginary portion of it.
So L is Z.
L is Z in this case, yeah. Okay, so, and the same way you found the x component of vectors is the same way you're going to find the real component in complex numbers. In the same way you found the y part by using sine of the angle, you find the length. And right here is our magnitude p. So this form, we call this the rectangular form. So our real plus our imaginary is our rectangular form, the same thing as with vectors. We also have our polar form. Our polar form requires a magnitude and an angle. You guys remember that from vectors? All right. So in order to find the magnitude, we're going to use this equation. The magnitude of p is equal to L, which is the square root of the x component squared and the y component squared, or the imaginary and the real component. You want me to go back? Yeah. All right. My bad. It's very similar to vectors.
So what part of the engineering will we be using that if they're basically the same thing?
Well, I guess it depends on the field of engineering you're going to. Like, from my knowledge, which is in electrical, we use it for AC current. It's a representation of AC. We're going to have complex values. Also, signals uses a lot of the real and imaginary plane, and it applies it a lot. I'm going to be applying it a lot in my research right now. And it's just some basic mathematics, so you'll definitely use it, and it will come in handy.
Just a question. What kind of engineering are you in?
Electrical.
I thought it was
Sorry.
mechanical.
But you would use vector notation, I guess, in mechanical engineering versus electrical. Do you still need to copy that down, or you go? Yeah.
So is this the formula you used if you had an imaginary number to begin with?
Say that again. So if you had an imaginary number,
-1 times the square root of -1 is -1.
yes,
This gets rid of the imaginary portion.
yes, but
And this is Pythagorean theorem.
yeah, it is in a sense, but it's not getting rid of complex numbers though. It's just a way of representing the complex number, or the complex. So, I guess your question is if you had like -17, square root of -17, right? Or just some arbitrary square root. I guess this is just a way of representing that graphically, and you would have your imaginary and your real component. So, -17 though is completely imaginary. There's no real part of that. So that would be contained all on the imaginary plane. So it would be at a 90-degree angle. So complex numbers are numbers that contain both imaginary numbers and real numbers. A real number is any integer, or any number at all, 0 through infinity, or -infinity to infinity. Yes.
So just go over the imaginary plane again.
All right. So Z, the same way we thought about it as vectors, right? So we had, this example is a good example. We have one link. We have a one-link robot right here of length L. Well, the formula for the imaginary portion is Z, and this is represented in the rectangular form. So you have your real component, which is everything contained along the real axis. So essentially it's just the x component if you're relating it to vectors. Your imaginary component is going to be your y component of this line. So, and this kind of just demonstrates it, but the only difference is this right here is the imaginary instead of just the y-axis, and this is the real instead of the x-axis. Okay, and this is the polar form of it. So we're representing the polar form as a magnitude and an angle. So we can represent it in two different ways. We can represent this line or vector z as a real, or I shouldn't say vector, I should say complex number, complex value z, as either a rectangular form or a polar form, which is the magnitude of z at an angle. And how do we find that angle? The same way you would think about it as this is a triangle, right? This is a right triangle. So how are you going to find the angle of a right triangle? There's a couple different ways, but if you're given just the length or the magnitude, or I'm sorry, if we're just given the x and y components and we want to convert, because this right here, this rectangular form, right, is just the x and y component. So if we're given this and we want to convert to polar form, what we're going to do is first take the magnitude, which is the square root of both components squared, and to find the angle, we're going to do what? Yep, the arctangent of our y component over our x component, or our imaginary component over the real component. And we can also write it in an exponential form, which is sines and cosines. So we have our magnitude, and we can represent it as, essentially, if we have this polar form and we want to convert back to the rectangular form, we're going to use these two equations, or one or the other equation. So this, P, our magnitude, which we have right here, times the cosine theta, that's going to give us our real component. This is the real part right here. And J times the magnitude times sine is our imaginary portion. So we would do this to go the opposite step. If we wanted to go from polar to rectangular, we're going to apply that equation. And the reason why they call it exponential is because the cosine of an angle plus j sine of the angle is an exponential of that angle. And this is known as Euler's formula, which we use a lot in signal processing. Euler's. Euler. Oh. Yes.
Is J always going to equal the value of square root of -1?
Yeah. J is always going to equal that value. Can't give you a definitive answer on that, but it is. Everyone still copying this, or we good? Does this make sense so far? Is anyone? I mean, yeah. The exponential? Okay, this I don't think you're going to need to worry about too much, but it's just another way of representing it. So, and this right here, down here, kind of shows that you can represent it as either this notation, or you can have it as z is equal to the exponential of j omega. And this all comes from Euler's formula. His proof for defining this, I don't know, but essentially just remember that the cosine plus j sine of theta is going to equal e to the j theta. I don't know if you'll need to know anything about the exponential yet. Maybe later in the class we're going to be taking the derivative and integrals of e, and then we'll explain that, but that's not till chapter 8. Chapter 8 or chapter 9, so we got a little ways before that. Yeah.
What's the proof of that?
Of Euler's formula?
Yeah.
The proof is derived from no, it's differential equations. I don't think derives the proof of it. but they do use Euler's formula in differential equations. I don't know the proof off the top of my head, truthfully. Just accept it as is. That's all. That's a lot of what this class is going to be. Accept it for what it is. Later down the road, you'll start going into why things are the way they are. So.
When it comes to like putting things in polar form, you put the so if the angle, I mean, if theta was 35, hypothetically, right?
Yeah.
And P with lines and it was 14. Well, the magnitude was 14.
Yeah.
So it would be this hypothetical would be 14 angle 35.
That's polar form, exactly. And that equation is going to get you to rectangular form.
Okay.
Yes.
So when you say multiply theta sine theta, I'm saying multiply sine theta.
Negative square root, or the square root of -1. But you don't have to, I guess you can't physically type that into your calculator because your calculator is not going to accept the square root of the negative number. So you have to just leave it as this form, because it's a complex number, it's an imaginary number. So you have to think about it as two separate values or separate quantities. You're going to have your real portion, and then you're going to have your imaginary portion of it.
So then you can calculate the real
Portion as is, yeah. Well, that's essentially what we're doing, is we're calculating the real portion and the imaginary portion. And that's making up our complex number line or vector along the imaginary or the complex plane. Does that make sense? All right. Yeah, so this is pretty much saying the same thing, that the point right here can be represented either as a vector or a complex number along the complex number plane. So this is vector form, this is the vector notation right here, and we see the similarities in the complex number form. They're identical, minus this I hat and j hat, and this j value. There's the polar form. Here's the exponential form, which is the same thing as the polar form. It just has an e to the j theta, where theta is your angle. So the representation of this, really what we've learned, understanding the polar portion and rectangular portion, and understanding how to convert between the two, and this imaginary plane, and this slide is really all you need to know to be able to do all of your homeworks and really understand enough of it for the exam. I think the next couple slides will probably be doing a couple examples. You good? All right. All right, here's an example in circuits when we would use complex numbers. We would use it for impedance of an inductor. So an inductor, which is an electrical component, is represented as Z, which is the impedance of it. So I don't know if you guys, if we went in the first lab, we had resistors in our circuit, right? Well, resistors, and we had a DC current or a DC voltage. Well, this would be for an AC voltage, which is a sinusoidal voltage, where your peak will be, let's just say, 10 volts to negative 10 volts. So this sinusoid is not the same as a DC current, where DC voltage is just, you go from 0 straight to 10, and it stays that way. So these are two completely different signals, essentially. So the resistor works in this system, works in both systems, but the resistor is just represented as R here. Well, we can think of impedance, or L, as resistance in an AC circuit. So, and Z is represented as J omega L, where L is the inductance, omega can be thought of as an angle or phase, and J is your imaginary component, or a complex component.
J is a complex component.
Mm-hmm.
And L is what?
Your inductance. Omega is your angle, essentially. Your angular frequency. So this example has, it wants us to find Z, given this equation. So Z is equal to J omega L. We're given L, we're given omega, and we're given F. Omega, the angular frequency, is F is your frequency, but it's your frequency in hertz. Where omega is your frequency, but it's your frequency in radians. It's something that, don't worry about it too much right now. It's kind of a little bit outside the scope of the class, but it's not difficult to understand.
Where's
J
J?
is, we know what J is already. J is square root of negative 1. We're just completely, so this value right here,
Or I thought it's like,
it's not, it is a constant. J is a constant. It's a constant square root of negative 1, but it's only our imaginary part, right? So this equation right here, Z is equal to J omega L, this Z value is supposed to contain a real and imaginary portion, right? Real and imaginary part. So what's the real part of this equation right here? 0. 0. There is no real portion, because J contains all of the imaginary. So along this graph then, this Z is just going to be at 90 degrees. It's contained only in the imaginary axis. There's no real part of it. So that will always be 0. Well, the real part is 0 for this equation. So now we just plug in our values right here, and this gives us Z is equal to 3 pi J. And that's only the imaginary part, or the imaginary portion. There is no real portion. So we can, if we wanted to represent this in rectangular form, we could just write this out as Z equals to 0 plus J of 3 pi, right? 3 pi ohms. And then, I don't know if it asks us, it might be doing that, but that's how we would represent it in the rectangular form. So, what would be your guess as to, what would be your guess to convert that into polar form? What do we need if we want to represent something in polar form? We need an angle and we need a magnitude, right? So how do we find the magnitude of that? The square root of both values squared together. That's going to give us our magnitude. So really it's just the square root of the imaginary portion squared. So it's just going to be 3 pi is going to be the magnitude. And the angle, since we have no real portion, what do you think the angle is going to be if we come back here? 90 degrees, exactly, because it's contained only in the imaginary portion. So if there's no real value, it's always going to be negative or 90 degrees. If there's no imaginary value, what do you think the angle is going to be? 0. The angle is 0. So those are two things just to remember. So the impedance of a capacitor is represented by this equation again. So off the bat, does this have a real component? It does. What, you saying yes? it's just J. There's only a J component in here, so it just has a imaginary component. So to find Z, how are we going to find Z? We're given our values. We're going to just plug this in, right? Okay, we're given F. So if we're just given F and the equation requires us to do omega, we have to remember that omega is equal to 2 pi F. 2 pi, our frequency in hertz. And this is going to be equal to 120 pi radians a second. And so Z contains only an imaginary component. There is no real component. Does that make sense? Yeah.
Is that always
It depends in what. For the impedance, yes. The impedance is going to be represented as a complex number. But that's for an AC circuit. The DC circuit, I don't think it has impedance. Don't quote me on that. And I should probably know that, but I don't. But for AC, yes. Yes, the impedance is always a complex value. So, is anything confusing so far? Or that you don't understand? Any questions? Yes. The capital F is frequency, but it's our frequency in hertz. So it's our, how do they call it? I forget the exact name. It's going to be like fundamental frequency or something along those lines. But yeah.
I don't get the solution. Because, like, you have 120 pi,
Yup.
and then, like, it disappears in the answer. What does it go?
Well, right here, they're just multiplying the 120 pi times 20 times 10 to the negative 6. So that's going to be a small number.
Yeah.
So 1 over a decimal number is going to be a number greater than 1, right? So if you have 1 over 0.5, that's going to be, what is that, 2.
Oh.
And that's how 132 is on the numerator now.
Yeah, it's 132, exactly, because this is going to be a number greater than 1, because it's 10 to the negative 6. Just multiply it into your calculator. I bet your calculator is going to spit out this value right here. And that's over J. But we could also bring J to the numerator by multiplying, it would actually become negative J. So if we multiply J to the top and bottom of that equation, we would have, what would it be? It would be 132 over J. If we multiply both the top and bottom by J, J times J is going to give us what? J squared, which is what? Negative 1. So we're going to have 132J over negative 1, which is just equal to negative J 132. So if you want to bring it from the denominator to the numerator, it's just J times a negative in front of it. Okay, that's what they did. It's the same thing I just went through. So we want to find the impedance of a resistor, inductor, and capacitor in series, right? So we know from the lab 1, right, that if we have 3 resistances together, what do we do to those resistances? We add all 3 resistances together if they're in series, like it is right here. The same goes for impedance. So we're going to add all of these together. So we have Z is equal to the impedance in the resistor, the impedance in the inductor, and the impedance in the capacitor. Where ZR is the impedance in resistor, and Z of L is equal to omega, or J omega L, and the capacitance is 1 over J omega C. So these are the three equations that we would use. So we're given R, we're given L, we're given C, and we're given F, which F we can then find omega from F. So let me just write that down on the board too. Omega is equal to 2 pi f, where this is our angular frequency. Angular frequency. And we could just call this the regular frequency for now. My handwriting sucks, I'm sorry. The book will probably call it something else, just in the book it's definitely not just called regular frequency. I can guarantee that. But that's the formula to convert it. And now if we were to do this, how are we going to do it? How would we go about solving this? First step. We would just add them, but we would put all of these equations together now. So we would have R, plug it in for R, this equation, plug it in for Z of L, and Z of C, plug it in there.
Then we have to find a common unit, so you can't technically add all of these different.
Exactly. We can't add, well, we can, because these are all impedances, right? So these are all representing impedances, which are units of ohms. But it's complex ohms. So we're going to have a real part and a complex part impedance. So it's going to be a complex impedance. So essentially it's the solution from the previous parts, right? So we know Z of L is equal to this, and Z of C is equal to that. So if we wanted to add them together, we have 100, which is the resistance, 100 ohms, plus 9.426J minus 132.6J. So our imaginary components we can just add up right there. So then we'll have our imaginary part as those two added, and our real part is just the 100. Yes.
How'd you get all that?
This from the previous problems. Remember how we found the impedance of the inductor and the impedance of the capacitor? Well, this impedance right here is the same value from the previous problem. So in this problem, this is what we solved for, right? And we went through the same steps, so you could go... So, alright, just to go back, what we're going to do is just plug in our values of omega and our values of L. We plug those values in, we then get our impedance of that component, the inductor. And the same goes with the capacitor. And then we add those two parts up, and we're left with this. So that Z is equal to 100 plus J of 9.426 minus 132.6. This will give us this value in rectangular form. So we have our real portion right here and our imaginary portion. So that impedance is a complex impedance. Yes.
So, if you had to go out to the store and buy something that would get you that impedance,
Mm-hmm.
how do you represent
What, the impedance? Well, a spec sheet will have the resistance or the impedance of it. So you can look at it and see, oh, all right. Well, I guess I shouldn't say that. It doesn't have the impedance. What it has is your inductance value, right? And your omega, you know from the frequency. So if you have an AC circuit, the frequency of an AC circuit's at 60 hertz. So you know the impedance just by plugging in your equation. So if you know your inductance, you can find your impedance of the circuit, knowing that the AC current is 60 hertz.
But that doesn't necessarily give you an imaginary equation.
It does. Because the impedance is represented as an imaginary number.
Always?
For an inductor, yeah. And for a capacitor as well. So then we want to find the polar form of this. So how are we going to find the polar form? We need an angle, we need magnitude, right? It won't be 100. It would be the square root of 100 squared plus 123.2 squared. Right here. Now if we want to find the angle, what do you think we're going to do? Very similar to right here. Or if we have the y component and the x component, or the imaginary component and real component, we're going to take the inverse tangent of the imaginary component, which is this portion of it, divided by the real portion. Arctan 2, it would be the function that you would type in MATLAB. Well, there is no j if we represent it in polar form. Just like in vectors where we didn't have an I hat or j hat when we represented it in the polar form, right? Because that's just telling us our magnitude and our angle. So I don't think there's that much more. Maybe there is. Maybe there is. I lied.
Like, it's good when I feel it when I do it on my own. I'm gonna be like, what?
No, I won't. So did that make sense? How from the start of the problem, yeah.
Yeah.
A-tan 2, isn't it y-x? Like, why is it?
It would be y over x, right? Y over x, yeah. It's not y times x. It's y over x, which is the imaginary over the real. Everyone have this copy down? Yeah, you take j out of for the polar form. There's no j. Well, like I said before, though, polar form can also be represented as an exponential form, which are identical. So your exponential form contains the j so that you don't lose that concept of j. So this would be more of a vector form. It is applied here as well, so it's a complex form. But and your angle. Exactly. I think the exponential form, it goes through it right here. So the exponential form is our magnitude still multiplied by the exponential of j to our angle. Okay, so our exponential form is our magnitude z, which we found right here, right? Times e, the exponential, which is the same as our polar form. It's still the same form. The only thing that's different is this e term, and it's e to the j theta. And the reason why that is because we have it as, we can think of from Euler's formula where it described sine and cosine, right? How do we find the x component? We use the x component is represented as what? Sine of the angle would find for the right triangle, if we're given z, right? To find this part, we use sine of that angle. To find y, we use the cosine of that angle. So that's kind of why they represent e to j theta is equal to the sine, or I'm sorry, I'm pretty sure it's 2. This might be 1/2 e is equal to the cosine of theta plus j sine of theta. Because why? Our cosine would be this component, which is our real axis, and j times sine, if we're finding the y component, is our imaginary. So that's kind of where this form comes from. So let me write out that z is equal to the magnitude of z at an angle of theta. This is equal to the magnitude of z, e to the j theta. Because our exponent is a constant and j is a constant, right? So the only two variables in both of these equations is z, our magnitude, and theta, our angle. It's just two different ways of representing it in the polar form. But they call this the exponential form, and this the polar form. Yes. Notation is notation. It really depends on what book you're reading, or what textbook you're reading. So, one may just put it strictly as polar form, and some may actually call this polar form. Like in signals, we refer to this as not an exponential form, but just the polar form. Huh? And he may ask you represent your answer as, like, kind of as this example, represent it as polar form, represent it as exponential form, but they're identical. The only thing that you have to write instead is this e to the j term. I'm not sure. I didn't look at the syllabus. Whatever the syllabus, the 9th? Alright. And it's probably going to cover the first 3 or first 4 chapters. No. I think this might be the last chapter on the exam. If I remember from last semester, the last question. Huh? Oh, do you have a review next class? Oh, are they? Oh, it was probably last semester's syllabus he gave. So, yeah, if I remember from the first exam, this type of question was the last question on that exam. Yes. I don't know. I'm not 100% positive. They're saying March 9th.
I'm getting my false dates. TA says he don't know, so he don't know. Don't come up with false dates.
Oh, it's the syllabus. You lost that bet.
You don't always go by the syllabus.
That's true. That's true.
So,
Alright, let's do... No, enough of this. Let's do another example. Alright, so this was an example of an AC, or actually this is just a current problem. So we have a current flowing through this, and the current, if we want to find V, which is represented by I times the impedance, we would, where we're given I as this angle, or as this complex value, right? So I is, this is in polar form, right? and this is our amps. Yeah,
I for curve, right?
I is current. Correct. And we're given, we know what Z is, right? From the previous problems, we know that Z, the impedance, is the impedance of the resistor plus the impedance of the inductor.
So it's 130.
130. No. Oh, yeah, it is, actually. I lied. You're right. I didn't look at this.
Did I say what?
No, it's not. I'm sorry, it's not 130. Because we have a real portion and imaginary portion. So the real portion is the resistor value, the 100. The imaginary portion is the impedance across the inductor, which is the 30.
So they stand on their own.
So they
It-
just be by themselves.
Remember that inductance is a complex number. Complex numbers contain a real part and an imaginary part, two completely separate. The impedance of an inductor is just the imaginary part. The impedance of a resistor is real, is the real component.
What is it, the impedance of what?
The impedance of the inductor is imaginary, and it's represented by that formula a couple slides back, which is J omega L. Yeah.
Is that all related to the fact that there's 10 volts and negative 10 volts for alternating current?
Yes. Yeah.
So the solution is 100 plus J30.
Is 100 plus J30. Exactly. That's what Z is. Because we're given the resistance and we're given the impedance across the resistor, we're given the impedance across the inductor.
So how come the last problem you added them all? We didn't have them in separate entities.
Well, we did. If we go back, so for this right here, right, we added all of the impedances together.
Yeah.
But we know that Z of L is an imaginary part, Z of C is imaginary, so we added the imaginary and we left the resistance as is, which is just real. So, coming back to this.
Okay, I don't get like when you turn it into radical -1 and then
You don't, you won't.
so what is it called?
It's just J. J is just the imaginary part of our complex number.
So you're actually not solving the equation, you're just putting it into this form?
Well, this form is solving the equation. Because it is solving the equation because we have a real component and an imaginary component, and it's represented on this coordinate system. The same way you would represent a solution, for example, the one-link robot. That is not on the imaginary axes or coordinate system, it's on a regular XY coordinate system. Well, the point was represented by a vector right there, and that's a real quantity, right? Represented of an X component and a Y component. That's the solution, right? Well, that's the same thing with complex numbers. That's the solution, but the J is just representing as an imaginary. If you think of things as everything as vectors, and just throw a J in there on the imaginary part or the Y portion of it, then you'll be fine. You won't have to worry about anything. Just think of it as vectors.
So complex numbers are initially the y-axis, and imaginary numbers are the imaginary numbers are the y-axis, and
Real numbers. Real numbers would be the x-axis.
real numbers would be the x-axis. So not complex numbers, but real numbers.
Complex numbers or complex solutions
They
consists of one real, one imaginary.
So the
Or
whole
real,
plane would be a complex.
it's a complex plane.
Okay.
Exactly. So, the real portion is just, is your x part, the imaginary is your y for the vectors. Coming back to this. plug in our values right here. We have 100 plus 30J, and this is our impedance, but we're trying to find V, right? So V is equal to I times R. That's the basics of Ohm's law. Well, Z is resistance. Impedance is resistance. So this is I times Z. Impedance is complex. That's the only difference. Impedance is complex, resistance is real.
Okay, so how you find V?
How do we find V? We're going to multiply both of these together, but we're given V, or we're given I in polar form, and we're given Z in rectangular form. So one or the other. And then you would change Z to polar form
No, change polar form
to
into
rectangular form.
Yeah.
Let's see if that's what they do. They might do both. Okay, so I is equal to 0.1, which is the magnitude, times the cosine of the angle plus J sine of the angle, right? From the first or second slide, one of those early slides, we gave the equation of converting from polar to rectangular. So now we have I as this. We have Z as this. So what do you think we're going to do to both the rectangular? Well, we're multiplying. So what we're going to do, oh, I lied. I'm sorry, we're multiplying. We are still multiplying. Here is our current, and here's our impedance. Now we would FOIL these, and this is what we would get. But it's nothing that you guys haven't done before, at least at this point of it. Once you have it, it's just multiplication, but it's multiplying two quantities together. And you would just FOIL that, and then you would just have to keep track of
Foil it and like
distributing this. So we would multiply this here, that there, that, add them up. Yes.
So the J squared cancels out with the J negative?
Well, J squared becomes what? -1. So that actually becomes real now.
Okay. That turns that 1.5 into negative?
-1.5. Then we would add up our real components, add up our imaginary components. So that we have, this is our final answer. Yeah.
you change the J into -1.
This is J squared.
It turns into -1, so you just -1 times. Oh, I didn't see the square.
Yeah, because remember that J is the square root of -1. So if we square it, we're going to have a -1 term. And this is rectangular form. And then if we wanted to represent it as polar form, we would find the magnitude and the phase using the square root of each value squared and the arctangent of our imaginary component over our real component. So that would be the result for rectangular form and polar form. Now if we're going to do polar form, we have to then convert Z into polar form. So this is going to have a magnitude and a phase as well. Which is represented here. And so Z is equal to the magnitude of these two quantities, square root of them squared, which is 104.4, and the arctan of the imaginary, the 30, over the real, the 100, is 16.7. And the exponential form is given right there. Now if we want to do V is equal to I times Z, our current times our impedance, what do you think we're going to do? Because essentially what V is also going to be in polar form. It's going to have a magnitude and an angle as well. We wouldn't add, but we would multiply our magnitudes, right? That would make sense to multiply our magnitude of I, which is this 0.1, times the magnitude of Z to get our new magnitude. But for our angles, it's a little different. We're going to add our angles.
So multiply the magnitude
Add angles. If it's division, you're going to subtract angles. So right here, we're going to multiply. Right here, we multiplied 0.1 times the 104.4, and we added our angles. We added the 30 plus the 16.7. And this gave us the polar form. Any questions on this? You'll probably see a question like this in the homework, possibly the exam. So definitely try and understand this problem. Are we good on this slide? All right. Okay. We good now? Alright, so here are a couple notes on it. Adding complex numbers is easiest in rectangular form. So if you have two complex numbers, it's easy to add complex numbers in rectangular form because we have our real component and we have our imaginary component already separated. So if we have two complex numbers, both with an imaginary and a real number, then we would just add the real parts and the imaginary parts. So right here, Z1, we have the real part of 1 plus the imaginary part of 1. And for Z2, we have the real part of 2 and the imaginary. So we would just add or subtract those real parts. If we're supposed to add or subtract them, just add them up, and the same with the imaginary.
So when we have to multiply and divide complex numbers?
Multiplying and dividing complex numbers is easiest in,
No, I'm saying when will we have to?
like the previous example, where we have a complex value I, the current, and a complex value Z, the impedance. And multiplying them via V equal to I times Z, and we want to find the voltage, right? So we're multiplying two complex numbers. I is complex and Z is complex.
But we just chose to use it both ways to get the same answer, so when...
You can use both ways, but the notes is kind of just explaining what's the easier way of going about it. You can see that there's less steps here than there are right here, doing it in rectangular form and multiplying, because we have to go through this process of distributing the two quantities and then collecting all our terms. You're more likely to make a mistake doing this than just multiplying your magnitudes and adding your angles. So multiplying is easier in polar form, and addition or subtraction is easier in rectangular form. And so this kind of goes through multiplying, dividing, is easiest in polar form. So, and like I said, if you're dividing two complex numbers, you're subtracting them. You're subtracting the angles. Does that make sense? For division. So if we have, for example, Z1 over, so an example of that would be if we wanted to find current, right? So if we have V is equal to, if we have V and Z as complex numbers, but we want to find current, we're just going to divide, V over R. And if this is a complex number and this is a complex number, we're going to subtract the angle between the two. And then another topic of this is complex conjugates. So what complex conjugates are just it's the negative imaginary. So if you have Z and you have Z conjugate, the values are the same except the imaginary number is a negative instead of a positive.
What does that star mean?
That star means conjugate, represents the conjugate.
So what is a conjugate?
A conjugate is essentially this. It's just the negative imaginary of it. So I guess in terms of, I understand it in terms of signals because that's the class that I took and it's a lot to go in depth, but say it again.
Like in a conjugate and conjugate that multiply by
The opposite, exactly. So if you're doing it in algebra, so an example is, give me an example, 1 plus x or something over 2 minus x. The complex conjugate, if we're multiplying it by, would be 2 plus x, right, over 2 plus x. So we're switching up the signs of our variable to cancel out, yeah. And that's the complex conjugate. That's what we would do it in terms of algebra. But for this, it's pretty much the same thing. It's just you're switching the sign of your imaginary component. And this pretty much goes through saying that z times z conjugate, the magnitude is equal to a squared plus b squared, the magnitude squared. And this is the math that goes through all of that.
But as long as we know that a squared plus b squared equals that, then we're fine. We don't really need to know how they got to that.
And pretty much what this is saying is this is a real number, right? A squared plus b squared is a real number. There's no j in here. So if you multiply a complex number by the conjugate of the complex number, you get just a real number. Just remember that. It's kind of, I don't know if he'll have any question like that on the exam. But he might now that I said that. Okay, and here's an example. So if we have C, which is equal to 3 plus 4j, and we want to find C times the C conjugate, we first need to find the complex conjugate, right? Which is just the sign flip. I'll do it through presentation. So the complex conjugate of 3 plus 4j is 3 minus 4j. We switch the signs of the imaginary term. And then multiplying out, we know what? instead of going through this process, we know that it's a squared plus b squared, where b is the 4. So this comes out to be 25. So c times c conjugate is equal to 25. And now we want to represent it as, it says find it using rectangular and polar forms. I guess this was the way of doing it through rectangular by multiplying the two. Oh, my bad. So our complex number c is in rectangular form for this problem.
How do we get number 16 if
Right here.
if
'Cause-
j equals -1?
Because j squared equals -1. So you have 4, which is your 16, and then the j squared is -1, so that will give you -16 minus a -16. Does this make sense? This problem? Alright. So for polar form, we just convert it doing our normal conversions, which gives us that. And now the complex conjugate of this is going to be equal to a negative angle. So in polar form, your complex conjugate is just going to be a negative angle instead of a negative imaginary part. Because if we had this, here's z, and then here's the complex conjugate z, z star, where they would connect if you go at it this way, but we have a negative angle instead. Yes. It would. So it would come out like that. And that makes sense, right? Because this is the imaginary portion of it. The imaginary part's flipped.
Would you ever not use things that come in the imaginary part?
Yeah, I guess resistance, because resistance is just real.
But we're working on impedance, right?
We're working on impedance, exactly. Yeah.
Is the J portion always going to be on top of the imaginary record of the Y?
Say that again.
When you do the arcane,
Mm-hmm.
the J portion, J coefficient, will always be...
Is always on top. So your imaginary part, or your J coefficient, is going to be on the top of your inverse tangent. And so if we wanted to find C times our complex conjugate of C, we know that it's easier to do things in polar form. It's easier to do multiplication in polar form than rectangular form. So we have 5 times 5, which is 25, and then we add up our angles, right? So our angle now is what?
You said what?
So what? No, if we so we want to find our complex number times the conjugate of the complex number, right? And we know that it's easier to multiply things in polar form. And here's our polar multiplication. So what do? We multiply our magnitudes of the two, which is 25, and we add the angles, which is 0, which is 0. Which is what they do right here. And this is 25 and an angle is 0, which is the same thing we got doing it in rectangular form. And this makes sense, because if we multiply a complex value by the conjugate of that complex value, these two values, the magnitudes are amplified, but the angles between them go to 0, so it's only a real part.
It's only different, like in algebra, it will end up being 1, because you know you don't Based like identity.
Say that again.
I'm just trying to play it up.
All right. Is that the last slide? Looks like it is. So, when we switch the sign of the imaginary part of the complex number in the rectangular form to get the complex conjugate, this flips the complex over the real axis, which is what I showed you guys there. And that's all I got for you. So.
That's fine.
This is gonna be on blackboard.
Yeah. So, I mean, we could start recitation now so we can end it early, if you just want to do that.